To meet the Paris Agreement target, the most important thing we must do is to stop emitting greenhouse gases. But stopping emissions, unfortunately, isn't going to be enough. And we're also going to need to actively remove carbon dioxide from the atmosphere. So modelling studies have shown that by the end of the century, we're going to actively need to remove about 5 to 20 billion tonnes of carbon dioxide from the atmosphere every year to meet that Paris Agreement target. And that's going to be an enormous challenge, because to put that into perspective, 1 billion tonnes of carbon dioxide is equivalent to the annual emissions from all cars and vans in the US, or the amount of carbon dioxide taken up by 50 billion trees each year. Weathering is a natural process that converts carbon dioxide into stable forms of carbon that have no greenhouse gas effect. So the weathering process involves dissolving atmospheric carbon dioxide into rainwater, and that creates an acidic solution. And so when that rain falls over land, it attacks rocks and it partly dissolves them. And the carbon dioxide during that process is converted into hydrogen carbonate ions that are either eventually captured in the ocean, or they can precipitate as carbonate minerals. And on a global scale, weathering removes about 1 billion tonnes of carbon dioxide from the atmosphere each year, and it plays an important role in the long-term regulation of Earth's climate. However, natural weathering and carbon mineralization take a lot of time. So in order to remove significant volumes of carbon dioxide from the atmosphere by the end of the century, geologists need to investigate ways to speed up those processes. So there are various ways to speed up weathering processes. And enhanced rock weathering involves applying freshly ground up silicate rock material to agricultural soils and harnessing the photosynthetic energy of the crops to increase weathering rates. As the mining industry produces billions of tonnes of ground up rock material every year, the waste material left over from that mine processing has the potential, if it has the right chemical composition, to be used as a feedstock for enhanced rock weathering. So model simulations have shown that if we apply around 1 to 5 kilograms of ground up silicate rock material per metre squared per year to agricultural land, and that's agricultural land that lies within 30 degrees of the equator, we could lower levels of atmospheric carbon dioxide by between 30 and 300 parts per million by the end of the century. The modelling studies have also shown that if the world's major economies, so that's the USA, India, and China in particular, rolled out enhanced rock weathering to between about 10 and 50% of all of their agricultural land, then between about 0.5 and 2 billion tonnes of carbon dioxide could be removed per year from the atmosphere. And so that equates to about 40% of the amount required by 2100 to meet the Paris Agreement target. The important thing now, though, is that we need to verify these predictions. So in Southampton and in Sheffield, we're undertaking large-scale field trials to quantify the amount of carbon dioxide in real life that's removed from these enhanced rock weathering processes. We're also looking at the effects of adding that ground up silicate rock material to the agricultural soils. We're looking at the effects on the crops themselves and also water quality. Some of the hydrogen carbonate ions that are produced as the acidic rainwater attacks the rocks and soils can also precipitate as carbonate minerals, essentially turning atmospheric carbon dioxide into stone. And this process occurs naturally. For example, carbonate veins occur in the Oman ophiolite. But by geoengineering carbonate precipitation, we could significantly increase the amount of carbon dioxide that's removed from the atmosphere. And one way we can do this is to pump carbon dioxide enriched water into permeable fractured basalts, such as those that we find on land in Iceland. And in fact, there have been a number of pilot experiments conducted in Iceland, and these have shown that more than 95% of the injected carbon dioxide was turned into stone when it reacted with that basalt within 2 years. The mining industry extracts tens of billion tons of rock material each year. And that generates huge amounts of freshly exposed rocks that could be used as feedstock for enhanced rock weathering and mineral carbonation. And so some of the work that we've done recently has shown that mine wastes have the potential to remove up to 4 billion tons of carbon dioxide from the atmosphere each year. And that's equivalent to the amount of carbon dioxide actually emitted by the mining industries each year. So as demand for raw materials continues to grow, implementing effective carbon dioxide removal schemes at mine sites will greatly improve the carbon footprint of the mining industry, and in fact may even make it a carbon negative industry. So I think it's important to stress that knowledge of these geological approaches to carbon dioxide removal is in its infancy, and it's really based on only a handful of pilot field studies to date. And we really don't know much about the long-term effectiveness, in particular on carbon dioxide removal. But initial work does show that carbon dioxide removal via enhanced rock weathering and mineral carbonation does have the potential to make a significant contribution towards achieving the Paris Agreement targets. Their cost is comparable to other carbon dioxide removal strategies. And as both techniques essentially involve speeding up natural processes, they may be less controversial than engineered climate solutions, such as, for example, cloud seeding and solar radiation management.